Hi guys, welcome to the K nearest neighbor lecture. K nearest neighbors, also known as KNN, is another very important machine learning model. This is used to solve classification problems. In this lecture, we are going to discuss the basic working principle behind KNN. KNN is widely used for classification and is one of the simplest among all the machine learning algorithms. The principle behind the method is to find a predefined number of training samples closest in distance to the test point and predict the label from these. In very simple words, KNN stores entire dataset as a training algorithms and categorize the test data points using stored information of its nearest neighbors. K is the number of neighbors. Let's learn with some example data. Let's consider we have a dataset with two classes, A and B, and the entire data, along with its features F1 and F2, are stored as a training algorithm. We want to predict the class for red, green, and blue test points. Based on the association with their neighboring points, it's straightforward to predict the class for red and green. The nearest neighboring data points for red are in B, so KNN will predict class B for red. The nearest neighboring data points for green are in A, so the KNN will predict class A for green data point. To predict the class for blue data points, let's discuss KNN with another simple example with fewer data points. So we already know the training algorithm is actually storing entire dataset in KNN. For predictions, KNN simply looks at the K points in the training set that are nearest to the test input. It counts how many members of each class are in the set and then returns the class with highest frequency as a prediction. So, the class with the most votes is taken as the prediction. In other words, the algorithm calculates the distance from the test point to all data points in the training dataset, sort the points by increasing distance from the test input into a distance matrix, and predict the majority class for k closest points. So let's go back to our question. The question was, which class the blue data point will get? If we apply the same principle as discussed above, for k equal to 3, we have a red dotted circle. There are 2 points from class B and 1 point from class A in the red circle. Class B will get more votes and our predicted class for blue data point will be B. For k equal to 6, we have a green dotted circle. There are 2 points from class B and 4 from class A in the green dotted circle. Class A will get more votes and our predicted class for blue data point will be A. Similarly, for k equal to 12, the predicted class for the blue data point will be B. So one very important thing that we have noticed, the value of k will affect the predictions. Selection of k is very important, and we will learn how to select k for our dataset in the practice section. KNN is simple and works quite well with small number of input variables, provided it is given a good distance metric and has enough labeled training data. However, the main problem with KNN is that it does not work well with high dimensional inputs. The poor performance in high dimensional setting is due to the curse of dimensionality. Let's try to understand this new concept of curse of dimensionality with a very simple example. Consider you have a straight line 100 yards long and you dropped a penny somewhere on it. It would not be too hard to find a penny along this 100 yards long line. You walk along the line and it takes 2 minutes. This one line is a single dimension. Now let's say you have a square 100 yards on each side. So you have 2 dimensions here. You dropped a penny somewhere on it. It would be pretty hard, like searching across 2 football fields stuck together. It could take days. So now, what if you have a cube with 100 yards along each side? This is hard. And we are only dealing with 3 dimensions in this example. It's like searching a 30-story building the size of a football stadium. So we see that the difficulty of searching through the space gets a lot harder as you have more dimensions. When the number of features or dimensions is large, there tend to be deterioration in the performance of KNN and other local approaches that perform predictions using only observations that are near the test observation, for which a prediction must be made. This phenomena is known as the curse of dimensionality. Let's try to understand the curse of dimensionality with a visual example. We see that if the dimension d is increased from 1 to 3, the number of regions of a regular grid grows exponentially in the space. The performance of our machine learning model or classifier is related to the number of features or dimensions. In the beginning, with increasing features, the classifier's performance increases until the optimal number of features is reached. If we further increase the features without increasing the number of training samples, the performance of the classifier is decreased. More the dimensions would be, harder it would be to search treasure box because more boxes would be empty. The picture above may help to understand curse of dimensionality. So we are done with the K nearest neighbor theory lecture. Let's move on and learn by doing. See you in the next lecture. Good luck.